Hey guys, this is lesson 19, and some of them I don't have, but I want to post something for you just to give you an idea. So let's start first by drawing the dimethyl pyrrolidine with two methyls at the 2 and 5 position. I believe pyrrolidine is a 5-member ring with nitrogen right there. Right, and then 2 methyls on the side, add my hydrogens right there, right? So I'm going to do my confirmation, my configuration. So I've got my first priority here. This is my chiral center. Got my first priority, my second, and third. So it's going counterclockwise. So this is S. Let's go ahead and check this one. I've got my highest priority up here, and then this is my second priority and my third. It's going right there to the right, so this one's good. So all I gotta do is turn it around and move that hydrogen and the methyl to switch positions. Okay, and I like to double check. So I've got highest, second, third, S, but the hydrogen's no friend, so that makes it R. So that's good to go. I'm going to move this over so I can draw my cyclohexanone, and that's going to be the ring with a double bonded oxygen on the top because it ends in -one, so we know it's a ketone. And then I'm going to check my notes. Okay, so basically that, okay, if I can arrange things in a better way. Basically, this nitrogen is going to come in and attach itself to the point where the oxygen's at, and it's going to then release the electrons back to oxygen. I'm going to roll that around, and then I'm going to go ahead and grab that the hydrogen, release those bonds. Wait, let's see. Do I want to release the bonds yet? If I release those, that gives a carbocation here. So I'm going to go ahead and do this, a double bond, and I can go ahead and take that hydrogen for the oxygen just to have a water molecule as a byproduct. And then we have a hydronium workup, so that's basically what I did here. I'm going to roll this around, and my nitrogen should have a lone pair. Oh, let me delete this water. So in the end, my nitrogen should have a lone pair. So I've got 1, 2, 3, 4, 5. It's got 5 electrons attached, so it's happy. And then this carbon has 4 bonds. This one has 1, 2, 3, 4. You just always want to make sure, like I always say, to check your bonds and make sure that you don't have any that have extra or not enough. Oh snap. Iodomethane, hydronium workup. Okay, let's go ahead before I move on, because I don't want to move on. I want you guys to see. So I didn't read the question because I'm exhausted from our exam. Basically, you also need to do the iodomethane and hydronium workup, but let's do that now so you guys can see. Please read the question. Okay. So actually this changes everything. So we're going to add the iodomethane. I'm going to use my hydrolytic function to make a positive or a carbocation arrange. And I get this. And then a hydronium workup. Okay, sorry, I'm at work. I would just start all over. I'm just gonna clear everything out and show you guys, and hopefully we can get the next one better, but what we end up with in the end would be something like this, with the hydrogen in the back and the methyl facing forward. So this would be our end product. Actually, let's see, 1, 2, 3, S, and we want to make sure it's R. So our end product would actually be the hydrogen facing forward and the methyl in the back. Okay, so this time we're going to read the whole question. We've got a 2-methylcyclohexanone, so I'm going to do my methyl and I'm going to do my double bonded O. And we know when LDA is after our cyclohexanone is added to the flask afterwards, we're going to be making the thermodynamic product, and that's going to be taken from this side. So all we're going to do is deprotonate and create a double bond. This then pushes the bond out of here. And then we're going to go ahead and add that iodomethane. So let me get my carbon and my iodine. Okay, so then I can go ahead and use this bond now to I'm gonna first do this, and then I can use this bond to go ahead and grab that carbocation and then go ahead and reform that ketone. Move it to the side. And lastly, make sure to delete everything and read the question again so that I don't skip a step. Okay, it looks good, so let's try it out. I'm going to try to go as fast as possible because I know that first question did slow me down a little bit. Okay, cyclohexanone. Pyrrolidine was the 5-member ring with the nitrogen, so now I'm going to change everything that I need to change. I'm going to add my hydrogens and move some things around. Okay, so I believe this is one now where we're going to replace the oxygen with the pyrrolidine. I'm double checking on my notes to make sure. And it says product. I want to make sure if it says product or products. Okay, I don't have it, but let's go ahead and try it out. I'm going to attach it at that carbon, which is then going to push the electrons back to oxygen. Let's see, I'm going to grab that hydrogen, create a double bond over here, and grab that so I can then go ahead and remove water. I'm going to delete this water molecule over here. Okay, it looks decent. I believe I actually do have this somewhere in my wrong notebook, but I'm at work right now, so I'm just gonna have to see which one it is because I don't have that notebook. Okay, so this is the answer. Okay, cyclohexanone and pyrrolidine, iodomethane, and hydronium workup. So this is going to be the same thing that we did in the beginning that I didn't finish the question. So the answer is going to be simple. That pyrrolidine is going to go and attach to the cyclohexanone and remove the oxygen, but then it gets added back. So I'm going to do this, and then I'm going to add a methane. Try to do like a shortcut, like and I'm going to look on my notebook. Okay, yeah, that looks about right. It doesn't mention in my notebook anything about configuration, so let's just try it out. Okay. So when you're doing this, if you like get the ones that say cyclohexanol and prolidine, you already know what it makes. And then looking at the other ones and seeing what they make kind of makes it a little easier to visualize. So I've got R2-methylcyclohexanone, LDA is at the end, so I know it's going to be replaced on the more sterically hindered side. I'm going to add my oxygen. And I'll just add my silicon and my carbons to that to make a trimethyl. Add my chlorine, add my hydrogens. I don't need to draw the LDA because it just basically serves as a purpose to deprotonate. But since it's on the LDA, or it comes into the flask after this, then we know it's going to make the thermodynamic product, which means it's going to form a double bond here on the more sterically hindered side. And then I'm also going to check my conformation. So I've got my first priority here, second, third. It's going counterclockwise, so I'm going to go ahead and press mirror. Pressing mirror doesn't affect this because there's no chiral center. So I've got 1, 2, 3 right there to the right. This is good to go. And I'm going to go ahead and roll this around. I'm going to deprotonate and create that double bond. That will then release the bonds back to oxygen. And then I'm going to go ahead and ionize this silicon and then grab it with the oxygen. I'm going to move this around, and this can actually, I think, be attached to the chlorine to create HCl. But for now, I'm just going to delete it. Okay, and yes, it looks weird because the steric hindrance, but since the LDA was added at the end, I like moving it just because it looks better. But since the LDA was added at the end, that's why, or after the cyclohexanol, that's why we have the steric hindrance. So I'm going to leave it like this. This is actually the problem he gave us during class. So if you didn't understand it, hopefully that helps a little bit. I think the placement of the LDA is really the most confusing part, but just remember, if it says LDA first in the question, you're going to be taking from the side that's not sterically hindered. Morpholine, I believe that is a 6-member ring with nitrogen and oxygen. Let me make sure, because I'm not 100%. Morpholine. Okay, yeah, so nitrogen, oxygen, opposite positions. And then we have our 2-methylcyclohexanol. I'm going to add my oxygen to that molecule, add my hydrogens, roll this around, and then I'm going to check for my conformation or configuration. So I've got my first priority, second, third. It's going right there to the right, so this is good to go. Oops. Okay, now I'm going to check my notes. Okay, so this is one that I was struggling with, but I think I've got it. Oops. So with this one, we're going to attach the nitrogen at the point where oxygen is. so I'm going to grab this bond where the hydrogen is connected and grab that, and that's going to then release the electrons back to oxygen. I can go ahead and grab that hydrogen, and then I'm going to go ahead and close it up on the more sterically hindered side. So I'm going to grab this bond so I can release the oxygen. I can go ahead and then grab that hydrogen that's by itself to create water. Oops. Okay, I'm going to delete the water now. Roll it around, and we get this funky looking molecule. And I don't have anything. I'm checking my bonds lastly. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5. Okay, so I think that should be good. This is one that I had to keep doing, and I had my notebook, of course, my wrong answers, and I finally put the right answer in my right answer notebook. Okay, cyclohexanone LDA, we know that that's going to take from, there is no sterically hindered side, so we just add a double bond on either side, add our oxygen, add our hydrogens, hit arrange and fit, and we see that this one has too many bonds because I added that double bond already, but that's why it's gonna come out of there. And then we're gonna add our trimethyl chloride. So I'll put S like this, and then I'll do my carbons to that. We already know that it's going to, the chlorine is going to ionize that silicon, and then it's going to be able to attach because it'll have that open space for oxygen to come and take it away. And of course, LDA, it doesn't matter at this point because either way you can put the double bond. But if we did have a methyl, then we would add this double bond in between the methyl and the oxygen because LDA goes into the flask after cyclohexanone. Okay, cyclohexanone, bromine, and acid catalysis. Let's see. Okay. So I'm drawing my cyclohexanone. I'll just go ahead and switch to oxygen, and then my bromine. Okay, let me move some things around. So it doesn't matter where you put it. It's not going to attach to the carbon with the oxygen. It's going to attach to one of these. So I believe if we wanted to, we could move this around like this, move this, take away one of the bonds from here, move it like this, reattach the oxygen to create that ketone, and at the end we get this product. Again, I'm sorry for going a little bit fast, but the first question really took up a lot of time, and that's my bad. Okay, so these aren't too bad actually. I found that what we're trying to do is just make everything have kind of a neutral charge. And to do that, we're going to, okay, sorry. Okay, to do that, we're going to move some things around, create double bonds, make that hydrogen go to nitrogen. So, all right, let's get started. So I'm going to create a double bond from one of these carbons to release a hydrogen that I can then go and take from nitrogen. I'm going to release those bonds from oxygen. And that's basically it. Everything's neutral. So I have 1, 2, 3, 4, 5. This nitrogen's happy. All these carbons should be good. I've got 4 bonds in this carbon, 4 bonds in this carbon, and I've got 1, 2, 3, 4, 5, 6, 7. I have a negative oxygen, but that's okay. And yeah, I think that was it for that one. These really aren't too bad. We're gonna put 2 because we've got just these 2 high electrons over here. I believe that was, okay, no. Okay, this is a perfect example of when LDA is in the beginning. Goes into the flask first. So I'm gonna add my 2 methyls, I'm gonna add my methane, I'm gonna do my oxygen, add my iodine, add my hydrogens, and for the most part, LDA is first in the flask, so we're going to be taking from the least sterically hindered side to create a kinetic product, release these electrons back to oxygen. And then we're going to attach this one. So I'm gonna go ahead and ionize. I'm gonna take this bond and attach the, what is that, carbon metal. I'm gonna create some HI. And then lastly, I see that my carbon here only has 3 bonds. So I'm gonna reform that ketone so it can be more stable. And I'll go ahead and delete my HI. And this is what we get at the end. So we've got a methyl on this side, and then we end up with a methyl on this side. I'm not too sure about if the conformation changes or if we need to worry about that, but in case it says anything, I guess we'll just do the mirror thing. Okay. Okay, now that is it. So I was gonna make another one, but I'm just gonna leave it at this. And remember the first one, I did put the correct answer in the end, but yeah, I did mess up a little bit, but yeah, good luck. Bye.